I cannot share the
We're
screen.
giving you so just a minute.
Okay.
Sir, now you can share the screen.
Okay. Can you see it? Yes?
Yes, sir. Yes, sir.
Thank you very much. So my talk is entitled 325 Years of Fractional Calculus. First of all, I would like to thank the chairman of the conference to invite me to give this talk. I am very pleased to be here to see many young people and very good researchers, plenary speakers, and presenters. First of all, I want to show you my journal, Progress in Fractional Differentiation and Application, an international journal indexed in Scopus, and I kindly invite you to send your best paper in the area of fractional calculus and application to this journal. Before starting the talk, I would like to give some important discoveries for the humanity. In year 2013, the Higgs field discovery reported by CERN, the Planck satellite observation of the background radiation, year 2015, the pentaquark discovery by CERN. Now, I would like to give the outline of my talk. First, the fractional calculus basic definition, then fractional calculus, some open problems, and the third one, some new direction. I am trying to present this type of calculus to be applied in artificial intelligence, to be applied in engineering problems, to be applied in modeling in mathematical biology. Fractional calculus deals with the study of so-called fractional order integral and derivative operator over real or complex domain and their application. Fractional calculus is actually a misnomer. The designation, integration and differentiation of arbitrary order is more appropriate. Many people discuss the fractional calculus during 325 years. The first who discussed was L'Hopital, who asked Leibniz if we can calculate the derivative of 1/2 of x. Then the Leibniz said, this is a very good question, it is a paradox, and sometime later good consequences will come. And indeed, he was right. I am not going to discuss the beginning of fractional calculus, very beginning, because the results were very simple. But I am talking about one paper of Liouville in 1832. This mémoire sur quelques questions de géométrie et mécanique et sur un nouveau genre de calcul pour résoudre ces questions. In this paper, he introduced a new type of fractional calculus and means that derivative of any order or an integral of any order. He here denoted the first differential, the second, the third, then the integral and of first order, second order, and then he tried to use the unify notation for the integral to distinguish the derivative and integral, but to make the same unification. So now he proposed to discuss the differentiation for any type of order, including irrational numbers and imaginary numbers. For example, he said derivative of 1/2 of y, integral of 1/2 of y dx to the power 1, 2. So that's why he said is the calculus of any differentiation and integration of any order, any arbitrary order. Okay. Now, why he introduced this calculus? Why do you need this fractional calculus? In order to solve some problem from mechanics, from geometry, he said, which cannot be solved according to the classical calculus. This was the problem. So he started to discuss the theory of this new derivative and integral. He said like this: we suppose that y represents a function of x, and we develop this function in power series. A1e to m1x, A2e to m2x. So when you take the derivative and integral of exponential, we obtain m to the power mu. Mu is positive, m here. If you take the derivative of this with respect to x, is m1, a1 e to the m1x. If you take the integral, it's a1 divided by m1. So you can write the derivative in general for any order, summation times m to the power mu. Mu is general, arbitrary. Also, integral is for mu negative. This was the basic idea. And then the problem is, okay, we define the arbitrary order. How can we apply to calculate some derivative and integral of any function? So he looked to the representation of 1 over x, integral from 0 to infinity of e to the minus alpha x d alpha. And then he calculated the derivative of any order of 1x. Is minus integral 0 infinity e alpha x, alpha mu d alpha. So he calculated. Then he calculated the derivative of arbitrary order of 1 over x to the power n. It is here, according to this formula. And then extend the derivative for any function. So he was able to start from a very simple derivative to calculate derivative and integral of arbitrary order for any type of function. So he, in a sense, he anticipated the Caputo derivative, which is today, for particular case, of course. Another derivative of arbitrary order is so-called Green-Valenikov derivatives. Green-Valenikov derivative is obtained as the limit of the limit of the limit So in the case n goes to infinity, this limit, we can express the derivative in this way. Summation k0 infinity alpha k u of t minus ka. So this is order of differentiation, and what we have that this derivative can be applied very good in engineering problems in artificial intelligence. Nowadays, the expression for the derivative and integral are given here. We have Riemann-Liouville left-sided fractional integral, Riemann-Liouville right-sided, and some formulas. And these are the derivatives. You see, derivatives are complicated. D over dx to the power n minus d over dx to the power n. Now, what is Caputo derivative? Caputo fractional derivative is very important, is used extensively in fractional calculus, and for application is very important. But it was introduced 53 years ago by Caputo in his paper, which has nothing to do with mathematics. This is Michele Caputo, and when he visited my university, this is Caputo when he was young, and this is called Caputo left derivative and right Caputo derivative. So it is actually derivative is addressed integral. We have the kernel, we have the derivative inside. So these are the derivatives of the Caputo type. Very, very much in fashion today. So we have classical derivatives, Riemann-Liouville and Caputo, mainly on Caputo derivative, this one, mainly on this derivative. We are going to use modeling in mathematical biology, application in engineering, using this type of operators with memory. These operators are singular when t goes to x because of this term. And now the problem is, how can we define another type of operator which has no singularity in the kernel? So Caputo and Fabrizio define a new definition of fractional derivative with a singular kernel in my journal, Progress in Fractional Differentiation and Application in 2015. Then we extended this application in this paper by replacing the kernel with Mittag-Leffler kernel. And what we have a derivative, a Riemann-Liouville case and Caputo case, and associated fraction integral with it. So what can we do with these new operators? We can apply these new operators in modeling. We can apply this operator in mathematics to discuss new features of mathematics. Among the papers, I want to show you some of them on some new properties of fractional derivatives with Mittag-Leffler kernel with Aaron Fernandez. Series representation for fractional calculus operators involving generalized Mittag-Leffler function together with Professor Srivastava and Aaron Fernandez. Then a new fractional model and optimal control of a tumor immune surveillance with non-singular derivative operator, together with Amin Jarjarmi and Sajadi, and published in Chaos. Then on the nonlinear dynamic system with the generalized fractional derivative with Mitter-Leffler kernel published in Nonlinear Dynamics. And there is another type of fractional calculus which is based on discrete fractional calculus. Discrete fractional calculus is very important in application. For example, chaotic maps, discrete fractional chaotic maps can be used very well in encryption and decryption, and also in modeling, for example, for the cancer and many other type of models in mathematical biology. Among these discrete fractional calculus, I want to give you some papers. It is Riemann-Liouville difference on discrete domains with Professor Wu and Professor Xi, and discrete fractional differences with non-singular discrete Mitter-Leffler kernel. Some further results of the Laplace transform for variable order difference equations, and our patent with Professor Wu and his colleagues from China. So description of the function of the patent. Chaotic maps plays an important role in the information encryption, but the existing models are simple and can be easily decrypted. This patent proposes a new chaotic map, one kind of fractional difference equation with more parameters and complicated chaotic behavior, such that the secret space increases in image encryption. Much more important, the new map fast generates chaotic series and can be applied to encryption of big data. Now, what are the problems with fractional calculus? Open problems for young people, for all of us. The physical and geometrical meaning of the fractional operators. We know that we have a meaning for example, the first derivative, and we have a meaning for integral. But these physical and geometrical meaning for fractional operators are not very easy. So we have to think how to define. Then we have the initialization of the fractional differential equation with Caputo derivative. So we use the same initial condition like for the classical differential operators, but these produce some contradictions sometimes. The other problems are finding new numerical methods for fractional ODE and fractional PD, constructing the correct version of fractional models to describe better the complex dynamics. These are the books if you are interested to study fractional calculus. Some books are very old, from 74, 75, Kilbas, Sanko and Marichev is in Russian 1987, but it's also in English. Miller-Rose, an introduction to fractional calculus, Kiryakova, Podlumny, fractional differential equations, Hilford, application of fractional calculus in physics, Kilbas, Sivastava, and Trujillo is very good. Theory and application of fractional differential equation. Lakshmikantam, Lela, and etc. from published in Cambridge Scientific Publishers. Mainardi, Tarasov, and these are my papers. The first book about fractional calculus model and numerical method is very good. There is a second edition. You can find many numerical methods and also mathematical biology. The other ones are given below. And the last one is about Lie symmetry analysis of fractional differential equation together with Mir Hashemi and published by CRC, Press Taylor, and Francis. Some basic questions about fractional calculus. There are several fractional operators. For a given experimental data, what is the appropriate fractional kernel which describe it better? The laws of nature are simple. Can these simple laws be appropriately described with the help of fractional operators? We have 325 years of fractional calculus. But still we have the following problem. What is a fractional derivative? Several answers are given below. First one is given by Bertrand in 1975. Then the last one given by me and Aaron Fernandez in 2019. And the title of the talk is on fractional operators and their classification. What is the modern fractional calculus? We try to organize a conference, online conference for 2 days about all these problems. We have discussed all these questions. We have 450 participants, and it's going to be in 4 to 5 December 2020. Now, some applications. Fractional variational principles, you know, very related to the control problems. This is an interview from Science Watch of Professor Ekavrabe and myself when the paper about this topic was published. It was considered a hot topic. Yes, indeed, it was the same because we obtain fractional Lagrange equation for discrete system. We start with the g of q, be a functional as follows, left and right derivative, and then in the Riemann-Liouville or even Caputo sense, then a necessary condition for j of q rho to admit an extremum for given function. Q of t is q rho satisfying the Lagrange equation for the following equation: dl over q rho plus db t b beta dl over da dt alpha rho q plus dat beta dl over dt b beta rho q is 0. This is actually, this type of equations are unique in mathematics. This type of equation can be applied to vibration and oscillatory system, and this technique can be applied in optimal control. These are some of my papers from very beginning. I am one of the pioneers in this field together with Professor Riwe, Oma Graval, Klimek, and so on. Fractional calculus in NMR, nuclear magnetic resonance. This is the first paper in the field with Professor Megin, which is top leader in this field. And we apply fractional calculus and we obtain better results. So we conclude that in biology, the fractional calculus is very important. We can apply it in immunology, for COVID, for any type of disease. We can apply the model based on these fractional operators because they have memory, and the memory effect is encapsulated better by these operators. Some new trends now. Fractional calculus in biology. I'll give you the first argument why fractional calculus is better. So what do we have to do? We have to compare the prediction of the fractional models with the classical models, and then we will see which one is better. Bolton in paper 1 has shown that fractional order model fits the particular data set with order 0.68 much better than the ordinary integer model. So this is a paper of Bolton on mathematical medicine in biology. And this is the experimental data versus the model. Prediction capability of proposed model. We have data set 6. 1, 2, 3, 4, 5, 6. Proposed model for mu is 1 in dash, means integer model, classical calculus, and proposed model for mu 0.68, which means that we have a fractional calculus. But what can we see? We can see clearly that here the fractional model are better than the classical one, but the fractional model is not the best in this Caputo representation. So we have to find some other kernels like Mittag-Leffler kernel, like derivative that I proposed together with Atangana in 2016. So that's why we are continuing to find new kernels. We are continuing to find new operators in fractional calculus to describe it much better the reality. But here, here the problem in mathematical biology is the following. The models are based, for example, on nonlinear ordinary differential equations. Now we have a classical ODE, for example. df over dt is a function g of t. When we apply the real data, we have to be sure that the dimensions are correct from the left and from the right hand side. From the left hand side, it is derivative. From the right hand side is g of t. For the classical case, there is no problem. There is a meaning for everything. But for the fractional case, there is a dimensionality problem. Plus, if you have a compartmental model for biological stuff, we have some parameters. These parameters have a meaning, biological meaning. So if you perturbate the left-hand side dimension, then the right-hand side dimension is perturbated too. This is the problem. So how can you solve this problem? We can solve this problem in several ways. For example, if you replace the first derivative df over dt with fractional df over dt, then the dimension is different. So I will give an example. Take f of t is t. Take the first derivative of t with respect to t is 1. Take derivative of t with respect, fractional derivative of t is not 1. So a correction factor should be added to the left-hand side. People are doing also in this way, but they also use the parameters to the power alpha on the right-hand side of the model. This is good, very good, but not always true, not always with a significance in the biological sense. So what I am trying to tell you, that in fractional modeling, we have to take care of many things when you try to compare with real data. Now, if you go to artificial intelligence and you put again data into the picture, we have to be careful with the dimension. Otherwise, if we are not taking care of the dimension, we have wrong result, wrong interpretation. So I am confident that in the area of modeling, in the area of applications of fractional calculus in engineering, for example, PID controller was generalized to already to fractional case and good results were obtained, but still is not on the market because it's not 25% better than the classical method, but the results are good. So we have huge hope to apply this type of fractional calculus to many engineering results, also in mathematics to describe new numerical methods. For example, to be developed, it is a big problem for fractional calculus due to the memory effect. And from the theoretical viewpoint, not all properties of, for example, maximum principle is not valid like in the classical case. So boundary value problems for ODE, initial value problem for PD, initial value problem for ODE. Many properties from the classical calculus are not valid in the fractional calculus. So we have to take care of the properties, the limitation, and the advantages of fractional calculus when we discuss a problem. I am very confident that if you apply this technique in all engineering science, in life sciences, all including biology, biophysics, and other fields, we will obtain very good results. Thank you very much for your attention. I am ready to listen your questions. Can you hear me?
Yes, sir.
Good. So I finished my presentation.
So can you hear me?
I am waiting for the questions. Yes. Is there any question? Can you hear me?
Yes, sir, we can hear you.
Okay. No problem. I am waiting for your questions. If you have questions, of course.
Okay, sir.
Thank you. Thank you very much. It was a great pleasure for me to be together with you. I wish you good luck to the conference.
Thank you, sir. Now I request Shilpi ma'am, Professor Shilpi Jain.
Yes, ma'am. Am I audible?
Yes.
Yes, ma'am.
Thank you, Professor Demetrio Bellano, for your valuable talk. If any researcher have any query, then you can ask from the professor. So there is no question.
Thank you very much.
So thank you, Professor Demetrio Bellano, for your wonderful talk and motivate our researcher and proposed a new problem in front of the young researcher. Thank you so much, Professor.
Thank you very much. Thank you very much. Wish you good luck to conference.
Thank you, sir. Thank you, ma'am. Now I request Dr. Mehchan sir to kindly invite Shilpi ma'am for her invitatory talk.
Thank you, ma'am. Uh, this is time to for the invited talk, Professor Shilpi Jain. Professor Shilpi Jain is currently working as a professor in the Department of Mathematics, Purnima College of Engineering, Jaipur. She completed a PhD from University of Rajasthan from Jaipur, and she has more than 18 years academic and research experience. Her research field is special function and fractional calculus. She has published more than 70 research papers in national and international journal of repute. She has interest, thrust area of her research area is mathematical in modeling, fractional and fractional differential equation, and its applications in various areas of engineering and science and technology, uh, problem solving and professional development, numerical analysis. She is also chief editor and editor of various journals, including SCI and Scopus Indexed. She has supervised four research scholars during her career. Now, I would like to invite Professor Shilpi Jain to deliver her invited talk in this session.
Thank you, Professor. Uh, Please provide me the screen sharing option.
Ma'am, kindly check.
Okay, ma'am. It's working now, I think.
Okay, ma'am.
शिल्पी मैम ने फोटो एनी की आ रही है मैम मेरे को थोड़े कोल भी एनी की आ रही है मेरे से नहीं करना
Screen is visible?
Yes, ma'am. Ma'am, it is visible.
Okay, ma'am. So, before starting my talk, first I'm very thankful to the organizer of the conference ICCTIM 2020 to give me opportunity to share my research with all of you, especially Professor Meher Chand, who is inviting me for such a wonderful conference. My talk is combination of applied mathematics and pure mathematics. In my opinion, it is very useful for mathematicians, physicists, as well as engineers. Professor Demetrio Bellano also start his talk, the definition of fractional calculus. So this is my topic, the fractional kinetic equation in terms of special function. The outline of the talk is abstract, introduction, generalized fractional kinetic equation, special cases, graphical interpretation, and conclusion. In this talk, my aim to present a new and further generalized form of the fractional kinetic equation involving generalized spatial function. The manifold generality of the generalized spatial function is discussed in terms of the solution of the fractional kinetic equation. The results obtained here are quite general in nature and capable of yielding a very large number of known and new results. In recent years, unified integral involving a spatial function attract the attention of many researchers due to various application point of view. For example, Professor Choi from South Korea and his collaborative team developed many research in this direction, such as Choi and Kumar in 2015 developed a paper, Solution of Generalized Fractional Kinetic Equation Involving Alpha Function, published in Mathematical Communication. The another is Choi and his group in 2013 developed a paper, Certain Unified Integrals Associated with Bessel's Function, published in Boundary Value Problem. Choi and Agarwal developed a paper, Certain Unified Integral Involving a Product of Bessel's Function of the First Kind, published in Honong Mathematical Journal. On the same way, research group of Romerio developed two papers in this direction. The first one is Romerio and Kruti developed a paper on fractional calculus of k-right type function. Another paper is Romerio LG and his group in 2014 developed the paper, The K-Basis Function of First Kind, published in International Mathematical Form. Hornbold work showed that the application of the present topic in astrophysics and space science. So Hornbold published paper in 1995, a heuristic remark on the periodic variation on the number of solar neutrino detected on Earth, published in Astrophysics and Space Science, and this the another paper is also published in Astrophysics and Space Science, which is the fractional kinetic equation and thermonuclear function in 2000. For my study, I required K-Pocumber symbol, which is given by Diaz. On hypergeometric function and K-Pocumber symbol given by the Diaz in 2007, which is published in this journal. Diaz and Periguin introduced the K-Pocumber symbol and K-gamma function defined as follows. Lambda nk is equal to gamma k lambda plus nk by gamma k lambda, where k belongs to R, lambda belongs to C except 0. Lambda nk is equal to lambda plus k 10 to lambda plus n minus 1 k, where n belongs to n, lambda belongs to C, the convergent conditions. They gave the relation with the classical Euler function as gamma k lambda is equal to k lambda by k minus 1 gamma lambda by k. Clearly, if we put k is equal to 1 in the equation number 1, in this equation, this equation reduces to the classical Pocumber symbol and Euler function respectively. In the another paper, Kruti in 2012 developed a paper on the K-basis function in International Mathematical Form in this direction. Recently, Romerio et al. Introduced the K-basis function of the first kind. For k belongs to R, alpha, lambda, gamma, mu belongs to complex number and real lambda is greater than 0, R mu is greater than 0 as follows. J k mu gamma lambda z is equal to summation of n is equal to 0 to infinity gamma nk by gamma k lambda n mu plus 1 minus 1 raised to power n z by 2 raised to power n by n factorial whole square. This is equation number 3 given by the equation number 3. Fox-Wright function psi p q z with p numerator and q denominator such as ai b j belongs to c, where I from 1 to p and j lies from 1 to q is defined by the equation number 4. Under the condition of equation number 5, which is j is equal to 1 to q beta j minus summation of I is equal to 1 to p alpha is greater than minus 1. In particular, when alpha is equal to beta j is equal to 1, where I is equal to 1 to p and j is equal to 1 to q, immediate reduces into the generalized hypergeometric function fpq, where pq belongs to n naught. This is given by equation number 6. In equation number 7, gamma nk defined by equation number 1, we introduce more generalized form of k basis function w k mu bc gamma z as follows, which is as you seen in the equation number 7, where lambda gamma mu c b belongs to c and real of lambda is greater than 0 and r nu is greater than 0. The importance of fractional differential equation in the field of applied science has gained more attention, not only in the mathematician, but also in physics, dynamical system, control system, and engineering to create the mathematical model in many physical phenomena. Especially the kinetic equation describe the continuity of motion of substance. The extension and generalization of fractional kinetic equations involving many fractional operators were studied by many researchers as follows. Sachev and Jaslowski M. 1997 developed a paper, Fractional Kinetic Equation on Solution and Application. Another paper is Saxena, Mathai, and Hubbard in 2002 developed a paper on fractional kinetic equation published in Astrophysics and Space Science. Saxena Kalla in 2008 developed paper on the solution of certain fractional kinetic equation published in Applied Mathematics Computation. This is the another paper. In view of the effectiveness and a great importance of the kinetic equation in certain astrophysical problem, the author developed a further generalized form of the fractional kinetic equation involving generalized k basis function. The fractional differential equation between the rate of change, the reaction was established by Howard and Mathai. The destruction rate and the production rate are as follows, which is given by equation number 8, which is first order differential equation, where n is equal to nt, the rate of reaction, d is equal to dn, the rate of destruction, p is equal to pn, the rate of production. And nt denotes a function defined by nt star is equal to nt minus t star, where t star is greater than 0. The special case of equation number 8, this is this equation for spatial fluctuation and inhomogeneities in NT, the quantities are neglected. That is the equation given by equation number 19. We solve this equation with the initial condition NIT is equal to 0 is equal to N naught at time t is equal to 0 and Ci is greater than 0. If we remove the index I and integrate the standard kinetic equation 9, we get equation number 10, which is NIT minus N naught is equal to minus C naught dt inverse NIT, where d naught t inverse is the special case of Riemann-Livoli integral operator defined as equation number 11. This is very important. The fractional generalization of the standard kinetic equation 10 is given by Hobart and Mathai are as follows, which is seen in the equation number 12, and obtained the solution of 12 as follows, which is nt is equal to n naught summation of k is equal to 0 to infinite minus 1 raised to power k by gamma of nu k plus 1 ct raised to power nu k. Further, Hubble and Mathai considered the following fractional kinetic equation: nt minus n naught ft is equal to minus c naught nu dt raised to power nu minus nu nt. Real of nu is greater than 0. where NT denotes the number density of a given species at time t and naught is equal to N0 is the number density of that species at time t is equal to 0. C is a constant where f belongs to 0 to infinite. By applying the Laplace transform to 14, this equation, Laplace transform of NTP is given by the equation number 15, where the Laplace transform definition is given in the equation number 16, which is Fp is equal to Laplace transform of Nt is equal to integration of 0 to infinite e raised to power minus pt ft dt. The objective of this work is to derive the solution of fractional kinetic equation involving generalized key basis function. The result obtained in terms of mythic lever function are rather general in nature and can easily construct various known and new fractional kinetic equations. In this section, we will investigate the solution of generalized fractional kinetic equation by considering generalized k basis function. The result are given by the this is our theorem number 1. If d is greater than 0, mu greater than 0, lambda gamma mu c v belongs to c, k belongs to n, r lambda is greater than 0, r nu is greater than 0, then the solution of the equation is given by equation number 17 is given by the following formula, which is given by the equation number 18, where the generalized mythic lever function E alpha beta x is given by Viam A in 1905 in this paper, which is published in Acta Math. The generalized mythic lever function E alpha beta x is given as summation of n is equal to 0 to infinity x raised to power n by gamma alpha n plus beta. This is the proof of theorem number 1. This theorem, the Laplace transform of Riemann-Livoli fractional integral operator is studied by Hobbold and Mathey in 2000. Laplace transform of d naught t raised to power minus nu ft is equal to p raised to power minus nu fp, where fp is defined in equation number 16. Now applying the Laplace transform to the both sides in equation number 17, we get equation number 21. 22, we solve the equation number 21, then we found the equation number 22, then after solving this we get the equation number 25. This is the result of NP. Taking Laplace inverse of equation number 25 and by using of inverse Laplace transform, p raised to power minus nu is equal to t raised to power nu minus 1 by gamma nu. Real of nu is greater than 0, which is given in equation number 26 as you seen. We have the result in which is given by equation number 27, and after solving we get the equation number 28, the solution of NT. And after solving we get the equation number 29 and 30. This is our theorem number 2. If d greater than 0, nu greater than 0, lambda mu, gamma mu cv belongs to c, k belongs to n, real lambda is greater than 0, r nu is greater than 0, then the solution of the equation is given by the 31. Of the equation 31 is given by the following formula, equation number by equation number 32, where e nu plus mu plus 2 n plus 1 is the generalized mythic lever function defined in the equation number 19. If a is greater than 0, d is greater than 0, nu is greater than 0, a is not equal to d, lambda gamma nu cv belongs to c, k belongs to n, and r lambda is greater than 0, r nu is greater than 0, then the solution of the equation nt is equal to n naught w k mu b c gamma lambda d nu t raised to power nu minus a naught nu dt raised to power minus nu, and t is given by the formula of nt is equal to n naught summation of n is equal to 0 to infinity minus 1 raised to power n c raised to power n gamma nk by gamma k mu plus lambda n plus b plus 1 by 2 gamma nu mu plus 2n plus 1 by n factorial whole square d nu t nu by 2 mu plus 2n. Multiply by e raised to power nu plus 2n plus 1 minus e raised to power nu t raised to power nu as you seen in the screen, where e mu plus 2n plus 1 is the generalized mythic lever function defined in the equation number 19. The proof of the theorem of 2 and 3 would run parallel to those the theorem number 1. As we simplify the 1, we same as the parallel line of theorem number 1 and 1 for theorem number 2 and 3. If we choose these are the some special cases. If we choose b is equal to c is equal to 1, then the generalized key basis function reduces to the following form. Wk nu gamma lambda 1 1 z is equal to b is equal to c is equal to 1. Then this is equals to z by 2 raised to power nu gamma summation of n is equal to 0 to infinity minus 1 raised to power n gamma n k by gamma k lambda n mu plus mu plus 1 z square by 4 raised to power n by n factorial whole square is equal to z by 2 raised to power nu j k mu gamma lambda z square by 2, where lambda gamma mu belongs to c and r lambda belong greater than 0 and r nu greater than 0. Corollary: if d is greater than 0, nu is greater than 0, lambda gamma mu belongs to c, k belongs to n, and real lambda is greater than 0, real mu is greater than 0, then the solution of the equation nt minus n naught t by 2 mu j k mu gamma lambda t square by 2 is equal to minus d naught nu dt raised to power minus nu nt is given by the following formula, which is given by the equation number 37. If d is greater, this is another corollary. If d is greater than 0, nu is greater than 0, lambda gamma mu belongs to c, k belongs to n, and r lambda is greater than 0, r mu is greater than 0, then the solution of the equation nt is equal to n naught d nu t nu by 2 raised to power mu j k mu gamma lambda d raised to power nu t raised to power nu whole square divided by 2 minus d nu naught d t minus nu nt is given by the following formula, which is seen in the equation number 39, where e nu plus 2 n plus 1 is the generalized mythic lever function as we discussed earlier. If we choose b is equal to minus 1, c is equal to 1, then generalized k basis function reduces to the k right function associated with the following relation, which is in the given equation. Then the theorem 1, 2 and 3 reduces to the following form. This is the another corollary. If d is greater than 0, nu is greater than 0, lambda gamma mu belongs to c, k belongs to n, and r lambda is greater than 0, r mu is greater than 0, then the solution of the equation nt minus n naught t by 2 raised to power mu w k lambda mu gamma minus t square by 2 is equal to minus d naught nu dt raised to power minus nu nt is given by the following formula, which is given by in equation number 44. Another corollary is if d is greater than 0, nu is greater than 0, lambda gamma mu is belongs to c, k belongs to n, and real lambda is greater than 0, r nu is greater than 0, then the solution of the equation nt is equal to n naught d nu t nu by 2 raised to power mu w k lambda mu gamma minus d raised to power nu t raised to power nu whole square divided by 2 minus d nu not dt raised to power minus nu and t is given by the following formula, which is given by equation number 46. Another corollary is if a is greater than 0, d is greater than 0, nu is greater than 0, a is not equal to d, lambda gamma mu belongs to c, k belongs to n, and r lambda is greater than 0, r nu is greater than 0, then the solution of the equation 47 is given by the equation number 48. By applying the result in equation number 1 to 4. After little simplification, the theorem 1, 2 and 3 reduces to the following form. If D is greater than 0, nu is greater than 0, lambda gamma mu CB belongs to CK belongs to N, R lambda greater than 0, R nu greater than 0, then the solution of the equation 4 is given by the following formula, which is seen in the equation number, this equation. The another corollary is, if D is greater than 0, nu is greater than 0, lambda gamma mu CB belongs to C, K belongs to N, and R lambda greater than 0, R mu is greater than 0, then the solution of the equation 51 is given by the following formula, given by the equation number 52. Another is, if A is greater than 0, D greater than 0, nu greater than 0, A is not equal to D, lambda gamma mu CB belongs to C, K belongs to N, and R lambda greater than 0, R mu greater than 0, then the solution of the equation, this and T is equal to this, is given by the following formula, which is seen in the screen, where this is the generalized mythic lever function defined, which is defined in equation number 19 earlier. Now, we make a graphical interpretation in this section. We plot the graphs of mean result established in equation 18, 32 and 34. Equation number 18, 32 and 34. This equation, equation number 32 and 34. Graph of the solution of the equation 18 are depicted below for some parameters values. That is, n naught is equal to C is equal to K is equal to 2, B is equal to D is equal to 3, mu is equal to nu is equal to gamma is equal to 1, lambda is equal to 1. We take lambda is equal to 1, 1.25, 1.5, 1.75, 2 in figure number 1, 2 and 3. For time interval t is equal to 0 to 1, t is equal to 0 to and t is equal to 0, 3 respectively. So here is the graph of the solution of equation number, this is the graph of figure number 1, this one. We take n naught is equal to C is equal to K is equal to 2, B is equal to D is equal to 3, mu is equal to nu is equal to gamma is equal to 1, lambda is equal to 1, 1.25, 1.5, 1.75 and 2, and we get t is equal to 0 to 1. So we get this graph. And in the figure number 2, we take n naught is equal to C is equal to K is equal to 2, P is equal to D is equal to 3, mu is equal to nu is equal to gamma is equal to 1, lambda 1, 1.25, 1.5, 1.75 and 2, and t 0 to 2. So we get this graph. And for this, we solution of this equation 18th, n naught is equal to C is equal to K is equal to 2, B is equal to D is equal to 3, and we take mu is equal to nu is equal to gamma is equal to 1, lambda is equal to 1 to 1, 1.25, 1.5, 1.75 and 2, and t is 0, 5. So we get this graph. And graph of the solution of equation number 32 are depicted below for some parameter values. N naught is equal to C is equal to K is equal to 2, B is equal to D is equal to 3, mu is equal to nu is equal to gamma is equal to 1, lambda is equal to 1, 1.25, 1.5, 1.75 and 2 various values in figure number 4 and 5 for time interval 0 to 0.05 and t is equal to 0 to 0.06 respectively. And we get this figure number 4 for n naught is equal to solution of equation number 32. For this values, we get this graph. And this is figure number 5 for this values, t is equal to 0 0.06. We get this graph. So it is clear from these figures that t is greater than 0 and the behavior of the solution for different parameter and time interval can be studied and observed very easily. It is also observed that if we select A is equal to D in equations 32 and 34, give the identical solution as we select in figure 4, 5, 6 and 7. This figure 4, 5, 6 and this figure 7. Figure 4 and 6, 5 and 7 represent identical solution as you seen in the figure 4 and 6. This is figure 4 and this is figure 6. They give identical solution and 5 and 7 give the identical solution. So I conclude my talk. In this work, we give a new fractional generalization of the standard kinetic equation and derived solution for the same. From the close relationship of the k-basis function with many special functions, we can easily construct various known and new fractional kinetic equations. Their relation to fundamental laws of physics is briefly discussed. So there are some references. Thank you.
Thank you, dear Professor, for your nice talk. If there is any kind of a query from participant, please put your query. And you can unmute yourself if there is any kind of question. You can put directly. Any question from the audience? I think there is no question from the audience. Dear Professor, thank you for your valuable talk on fractional kinetic equation and various type of applications of this fractional kinetic equation in other branches. Now, I would like to ask from Madam Shafali, please check the participant who is present here.
Yes, sir. Kindly, sir, allow me so that I can share the certificate for Professor Shilpi Jain. Kindly allow me to share screen.
Ma'am, just I will kindly raise your hand. Who is available for paper presentation?
Yes, I have arrow. The certificate of appreciation has been presented to Professor Valentina. Professor Shilpi Jain. And now please announce the participant to present the paper.
Okay, thank you, sir. Now, I request all the participants who are going to present their paper presentation, kindly raise your hands. So that we can cross-check who all are present right now.
Will raise hand. Raise hand. Become.
Okay.
Okay, thank you. Thank you.
Unmute yourself.
Hmm. Hmm.
Okay. Now I would like all the participants to kindly rename your name as your UID and your first author. For first paper presentation, I would like to invite UID with ICCTIM 206, and the title of the research paper is Optimal Demand Policy for Deterioration Item with Variable to Warehouse Demand. Kindly present your paper. I request ICCTIM UID 206. Title of the research paper is Optimal Demand Policy for Deterioration Item with Variable to Warehouse Demand. So kindly present your paper. Abdullah Al-Shami. Sir, are you present here?
Okay, Chandrali Vishnu.
Okay. I repeat once again, the paper presentation for UID code is ICCTIM 206, Optimal Demand Policy for Deterioration Item with Variable to Warehouse Demand. And the first author is Abdullah Al-Sami. Okay, then calling for the next is UID ICCTIM 204, and the paper research, title of the research paper is Effects of Prey Refuge, Additional Food and Fractional Derivatives on a Prey Predator Dynamics by Chandrali Vishal.
Yes, I am present here. Can you hear me?
Yes, I can hear you.
So can I share the screen now?
Yes, sure.
Yeah. But host disable participant screen sharing, it is shown. You have to allow me to share a screen.
Yes, I am allowing you.
Yeah.
I have allowed you. Kindly check.
This will stop other screen. Okay. So I think my screen is visible. Is my screen visible? Yeah. So I'll start the presentation. So my title, I'm Dr. Chandrali Bashir from Department of Studies and Research in Mathematics, Tumkur University. The title of my paper is Effect of Prey Refuse, Additional Food and Fractional Derivative on Prey Predator Dynamics. So Prey refuse and additional food provided to predator helps in balancing the population and ecology. So in this paper, we have taken a Hauling type 2 functional response, incorporating prey refuse and additional food and we have analyzed the dynamics in terms of existence and uniqueness and boundedness of the solution. Also, the necessary and sufficient condition of existence and stability of point of equilibrium are investigated. Also, we have investigated the global stability of the prey-predator dynamics, that means solution, and the numerical theoretical results are supported by numerical solutions. So this is what the abstract of the paper, and the outline of the paper we are going to analyze, or we are going to discuss this aspect of the prey-predator model. Okay, so mathematical I'm not going to take much time in introduction, and the one thing is what many researchers, mathematicians have done many studies of prey-predator model incorporating various functional response like Hauling type 2, 3, Beddington D-Angelis, and many other functional response they have incorporated. And with this functional response, that prey refuse and then diseases, infectious models, and the harvesting models, all these models are all investigated, and various models are also investigated in terms of incorporating fractional derivative also. So in the moreover, what is it in case this is what the basic model what Ma et al has introduced in case of fractional, it is a Hauling type 1 fractional functional response, logistic terms, and the prey refuse, which is indicated by M terms. So in our model, also one more thing what we want to say, I want to say here is prey refuse means it is hiding of the prey. So many times prey hides from the predator, and because of that predator may face problem to sustain in the environment. For that we may have to give some additional food to the predator. So this is what the whole model said about in this moreover, fractional calculus has very importance in case of good like important role in case of ecological model, because in a fractional calculus, the characteristic of fractional derivative is what it is defined in terms of integration. That means it holds the history of the past result. So because of that, in ecology it is very much important. So these are some of the basic formulas and definitions and lemmas we have used to prove our results. This is a basic definition of capitofractional derivative. It's important to mention then we have used capitofractional derivative in our model, and this is one Lipschitz condition for fractional differential equation. Because if the Lipschitz condition, it is in the ordinary also, if the Lipschitz condition is satisfied, then the solution exists and the solution is unique. That is what in fractional also that condition exists. Another lemma what we have used to show the boundedness of the solution. This is the one what we have used to show the global stability of the equilibrium point. And now comes to the main part of our problem, that is the model formulation. So we formulated a functional response with prey refuse and additional food to predator. Then a fractional predator-prey model is designed by incorporating this functional response. So these are the variables what we have defined is total time spent, handling time for each prey item, number of potential prey, this is X, Y is number of predator, V is the number of prey victim. Now, in this book, 1 minute, just I have gone ahead, I think. Okay, in this book, Mark Code has proved that the number of prey victim is proportional to both the number of potential prey and to the time available for searching. So in that case, this victim, V is the victim, is because T is the total time and this is the handling time. So that means this is the time available for searching. So this is the time available for searching of the prey. So this is for the, but one more thing is that because of the refuse term M, only X minus MX prey will be available for praying. So with that, the model takes the form of the functional response take the form of this. That means not exactly functional response. Now the victim is proportional to this, because earlier it was X, but now it is 1 minus MX prey will be available for praying. Now, another thing is the additional, this victim is inversely proportional to the additional food. So this is inverse proportionality. So if we find V from here, this is what the V we get solving for V, we get this one. So this is the functional response we have derived in this model. So this, incorporating this functional response, we have modeled this fractional differential equation, which represents a fractional predator-prey model with a prey refuse and additional food. One thing I want to request that when the time is over, please let me know before 5 minutes. So in this model, here, these are the terms. R is the intrinsic growth rate of prey, K is the environmental carrying capacity, eta is predator rate of potential prey, and then eta 2 is additional food, predation rate of additional food. E1 is the conversion factor after consuming potential prey. Also, we may say it as E1 as the nutrition value of the prey also, and E2 as the nutrition value of additional food. M is the refuse, D is the death rate of predator. Now, these are the questions what we are going to answer in our analysis. How the refuse affect, additional prey affect, nutrition quality of the additional food, all these things we are discussed in our analysis. So this is the boundedness we have proved using the lemma, what is already stated. We define the function W as this. So then take the this is the term what already we have defined in the lemma, exactly same thing we have written, and then replace W by the respective term, that means this term, and after the calculation we got this. And with this it shows that the function, the solutions are bounded in this set. So the existence and uniqueness, we try to establish the Lipschitz condition. So now we have to show that.
Please conclude your paper.
Pardon?
Please conclude your paper now. Time is over.
Okay, so I will just go to the then these are the existence of local stability of various equilibrium part we have given. I'll directly go to the numerical part. In the numerical part, we have discussed the various point of equilibrium, that means predator extinct equilibrium point, and here we have shown the effect of fractional derivative in the point of equilibrium in the dynamics. Again, this is for different condition of predator extinct equilibrium. Then the coexistence equilibrium point, the conditions are satisfied exactly with the parameter value, and this is what the profile of coexistence equilibrium point. And the prey refuse, here we have shown the prey refuse effect of prey refuse when the additional food is present. We can see the logistic, because in some of the papers what originally the equation number 1 is defined here, there we have seen in a different growth, but here because of the additional food the growth is logistic here. But in absence of additional food, we can see that when the refuse is increased, predator population goes to extinction. So this is what we can observe, the effect of additional food and the prey refuse, and also the fractional derivative in the defined model. And here are some of the references what we have I have stated, I have used. Yeah, I have completed the presentation.
Okay, thank you, ma'am. Anybody wants to ask any queries? Okay, thank you, ma'am.
Thank you.
Now I request UID with ICCTIM 206 optimal demand policy for deterioration item with variable to warehouse demand to kindly represent your paper.
Professor Abdullah Muhammad is not available here to present his paper, but he sent us his recording paper, and I am going to play here, and I will share the same at his place. So just please wait. I am sharing his paper.
Okay, sir.
Correct.
To present my paper on International Conference on Computational Techniques and Intelligent Machines with title Optimal Demand Policy for Declaration Item with Variable to Warehouse Demand. Contents of this paper: introductory literature survey, material and methods, mathematical model, total cost and output, the proposed model, results and discussion, conclusion and references in the last. Introduction: the optimal demand in the model of deteriorating atoms with demand variables represented by researchers as Ali et al. The downstream is assumed in the proposed model with permission and ordering a variable demand in temporary stock level. Wuhan and Hark applied the variable demand price of retail to obtain the optimal price to retail. Aparta et al. Assumed the linear demand variable inventory level and proposed the fuzzy model with 3 advanced algorithm solutions: material and methods, assumptions and notations. Here I will explain the assumptions. First one, the planning horizon is finite. Second, replenishment rate is infinite. Single atom inventory control. Demand is variable over the different time intervals. Deterioration is represented in demand model similarly in inventory model as constant. There is no replacement or paid of atoms in the period under consideration. The lead time is 0. The shortage is permitted. The inventory level at the end of planning horizon will be 0. The total relevant to associated cost aspects and purchasing, holding and shortage cost. three mathematical models. Here the demand is a variable and represented by two equations with two different time intervals. Here we need to find the optimal demand by find the solution for the equations of first and second. Here we find the optimal demand. After that, we were represented in the inventory level in the equation number 3 and equation number 4. Here the total cost and output the proposed model. Here total cost actually after the substituting the ordering cost and holding cost and purchasing cost and shortage cost, we got the equation of total cost in terms of small t1 and capital T. To find the optimal time, we take the partial derivative for total cost with respect to two terms. First one small t1 and second with capital T. Here we find the optimal time for capital T as T star in this format, and similarly we find the optimal time for T1 star in this format, and here we obtain the economic order quantity in term of T1, where T1 star we get it from the above step, and here also optimal shortage quantity we will obtain it because T1 star and T capital star we have it from previous step. Here results and discussion. The paper solved the variable when achieving maximum demand before shortage period and therefore the optimal shortage time. Similarly, the optimum length of planning horizon. The model represented the solution when shortage time is higher than known shortage time for deteriorating item in stock. A numerical analysis to output of the applied model. The 5 conclusion: the optimal shortage time and optimal planning horizon decreased when the deterioration was increasing, as the figure 1 I mentioned it in the original paper, and this is supported by real life. Second, the optimal demand is higher than the optimal demand without the shortage time with increasing in deterioration occurs. The third, the optimal shortage quantity is higher than the optimal quantity was out the shortage time because the issued order quantity in stock was less than known shortage time within increasing in deterioration possibility. References, I mentioned only 3 references because the short time. First one for Ali Dabata and Ayatollah Khalizada. They published this article with title "A Lot Sizing Model with Partial Downstream Delayed Payment and Partial Upstream Advance Payment and Partial Back Ordering for Deteriorating Items" in Journal of Manufacturing System. Wuhan and China and Hark Wang published the article with title Optimal Pricing and Ordering Policies for Retailers and Order Size Dependent Delay in Payment. They published it in the Computer Operations Research Journal. Third, Partha and Manas Kumar they published the article with title True Shortage Inventory Model of Accelerating Atom with Variable Demand and a Partial Credit Period in Applied Soft Computing. Thank you for watching us and good luck.
Thanks for his nice talk, and really it is appreciable. But the problem is that he was not available online. If he is okay, Abdullah, you can unmute yourself if you are now available. And if audience want to ask any question, please feel free to ask him. You can unmute yourself, and then after, once I want to check whether he is present or not. Abdullah, are you present here?
Yes, I'm here.
Yeah. If there is any question from the audience, please feel free to ask from him.
Okay. Any question, I'm ready to answer.
Yeah. Any question from the audience? Okay. Dear Abdullah, I have one question. Please let me know about its application in real life.
Yes. Actually, this proposed model deals with the inventory in stock when when the shortage time is higher than the non-shortage time, and I think that is applicable in real life, especially with the many deteriorating items like fruits and vegetables, because there is season production for that.
Okay, but in your paper, I want to show interested to know that if we want to establish some type of its computational result, so is it possible? Like
Yes,
other software?
yes.
Okay, so in your presentation, I did not see the computational part was missing. So if you introduce these computational part or numerical results and graphical interpretation, I think this will be more valuable for the reader. This is my kind suggestion for you.
Yes, but actually, yeah, I need to take time to open the paper because actually not ready now.
Okay.
But if it is essential, no problem. I will take time for that.
Okay, thank you very much for your nice presentation. Still, I want to know if there is any more participant is available here. He or she can raise hand so that that paper can be announced. There was 6 papers in this session, but only 2 paper has been presented here. Now you can proceed, Professor Shefali ma'am.
Yes, sir. Again, I want to ask, thank you, Abdullah sir, for your presentation. It was valuable for everybody. And now I request anybody else is there present who wants to present your paper in this session. Out of 6 papers, we have presented 2 papers. I'll be repeating the UIDs. If anybody is present in this session, kindly raise your hand. Okay, Khan Sana Rahman,
See, ma'am, I'm from session 6. Can I present paper now?
Let me ask.
Yeah, yeah.
Yes.
You can present your paper.
Can you please tell me?
Yes,
Can
yes,
you please tell me your UID?
ICCTIM 213.
Okay, you can present your paper.
Okay, I can present. So I'm having share option.
Okay, we are providing you the same. Okay, now the presentation for UID ICCTIM 213 and the title of the research paper is Numerical Analysis of Typhoid Model by Differential Transform Method.
Okay.
Presented by Khan Sana Rahman.
Okay, you just provide me the link for the share option.
Yes, we are providing you, ma'am.
Meher sir, kindly make the most. Meher sir, host बना दो. ये अगले दिन वाला है.
Okay, ma'am, kindly check. You can share the screen now.
Yes, yes, I'm trying.
Okay, ma'am.
Is it visible, ma'am?
Just a minute, ma'am. Right now it is not visible. No, ma'am, it's not visible right now.
No.
No, ma'am.
Now?
No, ma'am.
It is not visible.
No, ma'am, it's not visible.
Okay, 1 minute, again I will do it.
Take your time, ma'am, no issue. Yes, ma'am, now it is visible.
Okay. Now?
Yes, ma'am.
Okay. I myself Khan Sana Rahman, and I'm a PhD scholar at Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, Maharashtra. And I'm doing my research under the guidance Dr. Shiv Shankar R. Bidkari, Department of Physics, Shri Siddeshwar College, Majalgaon, Beed, Maharashtra, India, and Dr. Sadiq Ali Sheikh, Department of Mathematics, Maulana Azad College, Aurangabad, Maharashtra, India. And my paper topic is numerical analysis of typhoid model by using differential transform method. Now the contents of my paper is introduction, formulation and description of the model, differential transform method, application of differential transform method to typhoid model, conclusions, references. Now introduction. The differential transform method DTM is a computational method that can be used to solve linear or non-linear ordinary or partial differential equations with their corresponding initial conditions. Foucault proposed the concept of differential transform where the image of transformed function is computed by differential operations. This method is a numerical analytical technique that formalizes the Taylor series in a different manner. Differential transformation method is one of the well-known techniques to solve linear and non-linear equations. It was first introduced by Zhou for solving linear and non-linear initial value problems in electrical circuits. This method has been used to solve differential algebraic equation, Schrodinger equations, fractional differential equation, Lamé Emden type equation, free vibration analysis of rotating beams, unsteady rolling motion of spheres equation in inclined tubes. The benefit of this method is that it can be applied directly to linear and non-linear ODE without requiring linearization, discretization, or perturbation. Another important advantage is that this method is capable of greatly reducing the size of computational work while still accurately providing the series solution with fast convergence rate. The purpose of this paper is to use the differential transformation method DTM to systems of differential equation, which describes the VSCI RESRB epidemic model of typhoid fever and approximating the solutions in a sequence of time intervals in order to illustrate the efficiency of the DTM. The obtained results are compared with the ODE45 method. Now, the model formulation and description of the model. These are the model equation from 1 to 7, which describes the VSCIRESRB model. With initial condition, A0 is equals to A0, V of 0 is equals to V0, C of 0 is equals to C0, I of 0 is equals to I0, RES of 0 is equals to RES0, R0 is equals to R0, and B of 0 is equals to B0. Description of variables and parameters of the model are given below. Variables and description. V of t, number of vaccinated individuals at time t. S of t, number of susceptible individuals at time t. C of t, number of carriers individuals at time t. I of t, number of infected individuals at time t. RES of t, number of drug resistant individuals at time t. R of t, number of recovered individuals at time t. B of t, number of environmental bacteria concentration. Parameters and their interpretation. Gamma, equipment rate of susceptible individuals. Mu, natural death rate. Delta, disease induced death rate for I class. Delta 1, disease induced death rate for RES class. Delta 2, disease induced death rate for C class. Rho, probability that newly infected individuals are asymptomatic or carrier. Lambda, force of infection. Phi, resistant rate to treatment for carriers. Beta, resistant rate to treatment for infectious. Alpha, recovery rate due to prompt treatment. Sigma, recovery rate after second line of resistant treatment. Omega, waning rate of vaccine. Pi, rate of vaccinating individual in the susceptible class. Beta 1, transmission rate between S and C. Beta 2, transmission rate between S and I. Beta 3, transmission rate between S and RES. Theta, rate of transmission from carriers to infections. Beta 4, transmission rate between S and B. Sigma 1, bacteria shedding rate for C. Sigma 2, bacteria shedding rate for I. Now, differential transform method. The definition of operation properties of differential transform method from, this is given in this references, is given to utilize it in our model. The method consists of a given system of differential equations and related initial condition. These are transformed into a system of recurrence equation that finally leads to a system of algebraic equations whose solutions are the coefficients of a power series solution. The differential transformation f of k of a function f of x is defined as follows. F of k is equals to 1 by k factorial dk of f of x by dx xk, x is equals to 0. In equation 8, f of x is the original function and f of k is the transform function, which is called t function. Differential inverse transform of f of x is defined as f of x is equals to summation k is equals to 0 to infinity x raised to k f of k. From A and B, we obtain f of x is equals to summation k is equals to 0 to infinity x raised to k by k factorial dk f of x by dxk at x is equals to 0. Equation C implies that the concept of differential transform is derived from the Taylor series expansion, but the method does not evaluate the derivatives are calculated by an iterative way, which is described by the transformed equation of the original functions. Using equation A and B, the following mathematical operations can be obtained. This from 1 to 6, these are the operations differential transform method or the rules followed by the differential transform method. Even 7, 8, 9, 10 to 15, these are all the rules which are followed by the differential transform method. Now, application to VSCIRESRB model. Here, the differential transformation techniques is applied to solve non-linear differential equation system that arises from VSCIRESRB RB epidemiological model. Let V of k, S of k, I of k, IS of k, R of k, B of k denote the differential transformation of B of t, S of t, C of t, I of t, RES of t, R of t, and B of t respectively. Then by using the fundamental operation of this differential transformation method, discussion in section 3, which we will be there, we obtain the following recurrence relation to each equation of system star. So this we have applied to our model, typhoid model, and obtained the equation from 1 to 7, and consider the initial conditions. V of 0 is equals to 100, S of 0 is equals to 200, C of 0 is equals to 140, I of 0 is equals to 120, RES of 0 is equals to 80, R of 0 is equals to 60, B of 0 is equals to 0.01, and the parameter values be sigma 1 is equals to 0.9, sigma 2 is equals to 0.8, rho is equals to 0.3, mu is equals to 0.0080, mu b is equals to 0.0125, and sigma is equals to 0.75. Alpha is equals to 0.002, delta is equals to 0.052, omega is equals to 0.33, gamma is equals to 200, pi is equals to 0.6, gamma is equals to 0.6, delta 1 is equals to 0.011, delta 2 is equals to 0.01, sigma 2 is equals to 0.8, and here x1 is equals to omega plus mu, and obtained as a 0.338, x2 is equals to pi plus mu is equals to 0.6080, x3 is equals to sigma 1 plus theta plus mu plus delta 2 plus phi is equals to 1.1205, x4 is equals to sigma 2 plus beta plus mu plus delta plus alpha is equals to 0.8727, x5 is equals to sigma plus mu plus delta 1 is equals to 0.769, x6 is equals to gamma plus mu is equals to 0.3080, beta 1 is equals to 0.05, beta 2 is equals to 1.5, beta 3 is equals to 0.05, beta 4 is equals to 0.02. These are the values which are taken from different sources and assumed also. So the applying the initial conditions and parameter values in 1 to 7, we get the values of V1, S1, C1, I1, RES1, R1, B1. The closed form of solution where K is equals to 4 can be written as V of T summation K is equals to 0 to infinity T raised to K Vk is equals to the following equation. S of T, similarly we have calculated S of T, C of T, I of T, RES of T, R of T, B of T. These are the calculated part. Now comparison between DTM and ODE 45. In this section, we compare the numerical results obtained by ODE 45 with the results obtained by differential transformation method. We depict the figure of DTM and ODE 45 below. So this is the figure for the DTM, and where we have depicted V, S, C, I, RES, R, and B. And in this we see that the infected and carrier classes are increasing, whereas all other classes are decreasing or negligible. And in ODE 45 in figure 2, we see that we have used MATLAB to get the solution of the model. We got almost same results from both the methods. We found that in both the method V, S, RES, R, and B, there is negligible increase in the population with time, whereas C, I are steadily increasing with time. Conclusions. Differential transform method has been successfully applied to solve the VSCI RESRB typhoid model with given initial conditions. This method provides an explicit solution which is very useful for understanding and analyzing an epidemic model. Without any linearization, discretization, or perturbation, this method is applied directly to the system of non-linear ordinary differential equation. The comparison shows the efficiency of the method based on the numerical results. It can be concluded that by using DTM, we have approximated accurate analytical solution of our typhoid model. These are the references. Thank you.
Thank you, ma'am.
Dear audience, if there is any kind of question from your side, please feel free to ask. If there is any question. from the audience? I think there is no question from other side. Dear presenter, can you give me some application of your talk in real life?
This actually is based on the typhoid model.
Okay.
So I've applied it, the compartmental model of typhoid is given, and here I have tried to show the how the effective, if the infectious class or carrier class is increasing, the susceptible, the vaccinated, all other classes are decreasing. This is what then example which we can imply at in our real life situation, that when the infectious classes are increasing, this vaccination is decreasing. That means we have to take care more about vaccination and the susceptible classes, and how we can make use of some efforts so that we can control the infectious class by vaccinating or by taking some measures to control the susceptible class also. So this is what a real world problem only, that is typhoid model. It is an epidemic.
There is one question for computational part. If we use to compute these results, which software will be suitable for this computational part?
I've used MATLAB.
MATLAB.
Mathematica is also.
Mathematica is also suitable.
Yes, Mathematica.
And I think
Maple.
there is a Maple software that can be used for the computational part.
Yes, it can also be used. Maple also.
Okay.
But I have not tried it. I have used MATLAB.
Okay. Thanks for your nice presentation.
Thank you very much, sir, for providing the opportunity.
Welcome. Mrs. Sufali, please proceed the next.
Okay, sir. Anybody else who is present in this session wants to represent their paper?
I think there is no more for this session.
Okay, sir. Then I request Professor Shalu ma'am to kindly conclude the session.
Good afternoon to all. Thank you, Shafali ma'am. Thank you, Professor Shilpi Jain and Professor Dumrathu. First of all, on behalf of BFJ, I would like to express my sincere appreciation and gratitude to the chairperson, Professor Shilpi Jain, who chaired this session smoothly and expressed their valuable views. The theme of this session is innovative techniques and its applications in the field of mathematical modeling, biomathematics, and computational techniques in sciences. I would like to express my thanks to the presenters, Chandrali, Abdullah, and Khansana. The session is very interesting and appreciated by all the attendees. It is a useful interaction that is sure to motivate many aspirants. Sharing this experience with same of many leading researchers is a great opportunity for all of us. We are thankful for that. We look forward for the other sessions. Thanks to everyone. Thank you.
Thank you, ma'am. Thank you, all of you.